Hello everyone, welcome back to another video on context-free grammar. In this video we'll talk about the removal of null production a bit initially because there were not much examples in the previous video. We'll see one more example about how the null productions can be eliminated from a context-free grammar before we can move on to discuss the normal forms of context-free grammar, one of the most important topics under the CFG, right? So removal of null production, we know it is a part of simplification of CFG as we saw in the previous video. Now if you are given with a grammar like this, a context-free grammar like this, where we have got 6 productions for the 4 variables A, B, C, and if we have B gives lambda and C gives lambda as the productions, how are we going to eliminate them from the grammar? Okay, and the removal of null production or epsilon production is very tricky. As we know, we need to substitute this lambda wherever B is appearing on the right hand side of the productions. Similarly for C also we have one lambda production, so wherever C is appearing on the right hand side, we will try to substitute lambda for that. Okay, but we'll be doing that in a combination. Here we go. Okay, and first and foremost thing in the removal of null production is the identification of nullable variables. B is nullable, yes, we know, because it has a lambda production, B gives lambda. C is also nullable because it can be replaced with lambda. But A can also become lambda indirectly. If B is lambda, C is also lambda, A is going to generate lambda. So A is also nullable. So we have identified the nullable variables, right? And the point is, we are not going to remove the nullable variables altogether. We are going to remove only the null productions. Okay, we should be very clear in that, right? So we are trying to delete the production B gives lambda and C gives lambda, but without sacrificing the meaning of the CFG. Okay, to preserve the meaning of the CFG. What do you mean by that? It should be generated in the same language as it was before. Okay, so we are going to place lambda at the right hand side of the productions, or the right hand side wherever B and C are appearing. Okay, in the given set of productions, but again the substitution is going to happen in combination, right? If you take S gives A, B, C, D as the production, and we know B can be lambda, C can be lambda, A can also become lambda, right? We are going to substitute them one by one. Okay, so A, B, C, D will remain as it is. As we saw in the previous video, we cannot remove this production altogether because it has the ability to generate multiple strings, some other strings also. Here we are substituting lambda for only B. Here we are substituting lambda for only C. Here we are substituting lambda for both both B and C. Okay, here we have substituted lambda for A because A is also nullable indirectly, and here AB has got replaced with lambda. Here A, B, C, all those 3 variables are replaced with lambda. Here we have got A and C getting replaced with lambda. So we have covered all possible combinations. Alright, we have substituted lambda for every one of the combinations. Okay, so if it is ABCD, it will be ABCD. If it is A lambda CD, it will be ACD. A B lambda D, it will be ABD. A lambda lambda D will be AD. Lambda BCD will be BCD. Lambda lambda CD will be CD. Lambda lambda D will be D. Lambda B lambda D will be BD. Okay, so this is how the productions of S will look like after we eliminate lambda productions from the grammar. Okay, so the first step, we identify the nullable variables. We identified that A, B, C, all those 3 are nullable, and lambda was substituted for every one of the variables one by one, and the combinations were also in combination also. Fine. Then comes A gives BC, and if we substitute lambda for B, it will be C. Sorry. If we substitute lambda for C, it will be B. Okay. For B also it will be the case. For BB, it will be B followed by lambda, CC, C followed by lambda. So A gives BC, C or B. B gives BB or B, C gives CC or C. This is how the grammar will look like after we eliminate the null production. Okay, So this is how the null productions can be eliminated or will be eliminated from a given grammar. Okay. So now let's move on to discuss about the normal forms of GFC. What do you mean by normal forms? Okay, so far we have been talking about context-free grammar in general. Okay, and the general rule of a context-free grammar is on the left hand side we should have a variable, on the right hand side we can have the combination of variables and terminals, and we can have lambda also. Right. But when it comes to the normal forms, we have two of them for the context-free grammar. One is Chomsky normal form. We represent that, or we usually call it as CNF, and the exam papers or in the online materials you will be able to come across the term CNF often than the Chomsky normal form. And the other one is Greibach normal form, that is GNF. Okay, and when can we say this CFG is in Chomsky normal form, and what is the property of CFG so that it can be termed as a GNF? That's what we'll be talking about in the next two slides. Then we will also discuss about the procedure which will help us to convert a normal CFG into a CNF1 and a normal CFG into a GNF1. Okay, conversion of CFG to CNF, conversion of CFG to GNF. So those two are also important problems under this CFG concept. Okay, now let's understand when can we say a grammar is in CNF. We are talking about context-free grammar and the normal forms of CNF in CFG, that is Chomsky normal form. A context-free grammar G is in CNF, Chomsky normal form, if all the productions are satisfying the following form, or all the productions are of the form A gives BC or A gives A. A gives BC or A gives A. Can't we have any other variables? We can. So this final statement also should be included in the formal definition. So most often we try to omit this. We may tend to stop with these two, but here is the catch. Where A, B, C are in V. What is uppercase V? It is the set of variables. So left hand side we should have a variable obviously, but on the right hand side if we have only two variables or only one terminal, then the grammar is in CNF. So this property should be satisfied in all the productions. That is the point. Okay. So for instance, if A gives BC is one production, B gives A is another production, and A gives A is another production, and C gives B is another production. So this is in CNF, this is in CNF, this is also in CNF, but this is not satisfying the property of Chomsky normal form. So all the productions should satisfy the property of Chomsky normal form. What is that? On the right hand side we can have only two variables or only one terminal. We cannot have anything other than them. It's not like A gives B, C, D, or A gives A, B, A. These are all not in Chomsky normal form. We cannot have more than two symbols. We can remember in that way. Okay, the right hand side can have a maximum of two symbols. Those two symbols should be variables. Okay, if it has only one symbol, that should be a terminal. So A gives B is also not in Chomsky normal form. It should be a terminal if it is only one symbol. Okay, so A is in T, that's what it is mentioned here. This A will be part of the set terminal, and A, B, C are part of the variables set. This is Chomsky normal form for you. All the productions should be satisfying this property. Okay, then comes the Greibach normal form. It's slightly different than the previous one. A CFG is said to be in Greibach normal form again if all productions have the form A gives A alpha. What is that? A, no confusion, it is going to be from a variable. A, no confusion, it is going to be from the set of terminals. But alpha, if you look at the property of alpha, it is a bit different, right? Alpha is going to be 0 or more variables alone. V star, what is star? 0 or more occurrences of what? V. What is V? Set of variables, right? So on the right hand side of any production we can have a single terminal or a terminal followed by any number of variables alone, meaning A gives AB is not in GNF, Greibach normal form, whereas A gives AB is in Greibach normal form. A gives A, B, B, C, D are all uppercase. So these are all, this satisfies the property of Greibach normal form. Okay, the point is very simple. It should start with the terminal. After that, it can have any number of variables, 0 or more number of variables. Okay, so that is the property of Greibach normal form, and this alpha represents 0 or more number of variables alone. It cannot have terminals like this. It cannot have anything like this, A, B, T, A, B, no combination of variables and terminals will be allowed in the case of GNF. It should start with the terminal. After that, it should be only the variables alone in Greibach normal form. Okay, so CNF, two variables or a single terminal, GNF, one terminal followed by any number of variables. Fine. Now we are going to see the procedure with which we can convert a CFG into its equivalent CNF, Chomsky normal form grammar. Okay. Sorry. A context-free grammar is in CNF if it satisfies this property. Right. Now, can you tell me, or are you able to understand or identify whether it is in CNF or not? Is it in Chomsky normal form? I would say no, because S gives A, yes, absolutely fine, it is of this form. Z gives A is also fine, it is also following this pattern, but S gives A Z is not in the expected form. Okay, so we should have two variables or a single terminal. So these two are having single terminal, but here it is not having two variables. So this is not in Chomsky normal form. We need to convert that into its equivalent CNF, Chomsky normal form. Let's see how it is done. Okay, here we go. Here is the given grammar, and whenever we go for this conversion, we need to simplify the grammar first. Okay, simplify the grammar first. Step 1 should be simplification of the grammar. Okay. How a grammar CFG will be simplified? By removal of useless symbol, by removing null production, by removing unit production. Okay, but luckily for us, this grammar doesn't have any of these. Okay, there are no useless symbol, all symbols are useful. We do not have null productions, we do not have unit production also. So we are good to go. It is already a simplified grammar. Okay, but we are not going to touch these two productions because they are already satisfying the property of Chomsky normal form, but here it is not. Okay, so what can we do to make it to satisfy the property of CNF? This is the only problem, right? Instead of this A, if you are able to have a variable here, it will satisfy the property of Chomsky normal form. That's what we are going to do. Introduce a new variable like A1, uppercase A1. Okay, instead of this small a, we are going to use a variable A1. Okay, so what will happen? S gives A stays the same, Z gives A also will be the same. Instead of this A, we are going to make use of this variable. S gives A1 Z, and A1 A should be added to the grammar so that it is indirectly generating the same string. S gives A Z, right? But now this production satisfies the property of CNF because we have got two variables here on the right hand side. That is the property of Chomsky normal form, one terminal or two variables. So this is how we can make, or we can find the equivalent CNF of a given CFG. Okay, first step is to simplify the grammar. Then for variables we will be introducing, for terminals we will be introducing new variables if it is this case. Okay, that is example number 1 for you, where the grammar is already reduced. Now let's try to convert this into its equivalent Chomsky normal form. For that we need to identify whether it is CNF or not. No, it is not. These two are not satisfying the property, so we need to go for the conversion. For the conversion we need to simplify. Okay, simplification should take place first because that will solve a lot of problem like in this example. Okay, excuse me. And while simplification will identify the useless symbols. What are the useless symbols? If it is not appearing on the right hand side, but all the variables are appearing in the right hand side. And if you look at S gives A, no problem. S gives A Z, fine, it is connected with Z. Z gives AC, yes, fine. C gives AZ, yes, all variables are reachable. But if you look at these productions, Z gives AC, C gives AZ, it is forming a loop and they are not going to terminate at all. Okay, kindly refer to the previous video there where we have got something like this, S gives AA, where the grammars where the productions did not allow us to terminate. Okay, the each and every step we had an uppercase S. Same is the case with this also. Okay, Z will generate AC, C will generate one Z, Z will generate one C, C will generate one Z. There won't be any stopping for that. Okay, so these two are going to be termed as useless. Z won't be useful, C won't be useful. Sorry. And if you look at D, D is not at all reachable from the starting variable. Okay, from S we cannot go to D at all, so this will also be useless. So this production will be removed. Z gives AC, C gives AZ, D gives B. All those productions are going to be useless productions. And the only production remaining will be S gives A. Okay, and that will be the end of the elimination of useless symbols. And it doesn't have any lambda production, or it doesn't have any unit production also. Okay, so this is the only production remaining in the grammar, and fortunately for us it is already in Chomsky normal form, because in Chomsky normal form we can have a single terminal or two variables. So it is already in CNF, so that's it. Okay, so that is the reason why it is important to reduce the grammar or simplify the grammar first, which will solve most of the problem for us even before actually we start the conversion process. Okay, and I know it is a bit tricky to find C and Z as useless here, but that is the logic you need to have. That is how you need to think and find what are the useless symbols here. Fine, that's about this grammar. Then comes this one. S gives A, S gives AA, A gives B, B gives B. Okay, it is not in CNF. Let's go for the conversion. First step is simplification. Are there any useless symbols? No, there are no useless symbols, and we don't have any null productions also. But we have an unit production. Okay, but we have an unit production. A gives B. So A gives B. Instead of this, we'll have B. We'll substitute B. Okay, but if you do that, this will become useless, right? We won't be able to reach B at all. If you replace B with B, that's how the substitution rule works, right? If you remove and if you try to eliminate the unit production, this B should be replaced with the right hand side of this production, which is small case b, that we have done that. If you do that, this B cannot be reached from the starting variable, that will become useless. We can remove it from the grammar. Okay, so the production that we'll have will be S gives A, S gives AA, and A gives this small b. Fine. Now these two productions are satisfying the property of Chomsky normal form, no confusion, but this is not. So for this A, we can introduce a new variable as we did in the first example. We are introducing a new variable A1 gives A. That production should be included in the grammar. Okay, S gives A gives B, which were already there. This is the new introduction. S gives A1 followed by A, then A1 gives A should be added. And one of the common mistakes that most of us tend to make is we will introduce a new variable, but we will forget to introduce or include this production in the grammar. Okay, so whenever you are introducing a new variable, please write the production first, then add the new variable in the production. Okay, so that you will not miss out. So please don't miss out this. So if A1 gives A is not there in the grammar, then this production will be useless, because there won't be any production for A1. Alright, so please be careful. And one more example, S gives A, S gives AA, S gives lambda. Right, now this is not in CNF, we need to go for the simplification. Sorry, no useless symbols as usual, but we have a null production, A gives lambda. Okay, so if we substitute lambda for this A, we'll have S gives A alone. Okay, we don't have any other production for A also, so this production will go out of grammar altogether. Instead of A, if we substitute lambda, we'll have S gives A. That will be the only production available, okay, which is already in Chomsky normal form. Alright. Excuse me. Right. So please simplify the grammar first, then go for the conversion. That will help us a lot, as I keep on saying. That is what is the conversion of CFG to CNF. We have seen a few simple examples alone, but even if any complex examples or complex problems are asked, you can follow the same procedure, because sorry, we know how to simplify the grammar or how to find the reduced CFG, and with that we can most of the time we will be asked to introduce new variables alone. Right. But there may be some cases where, if we have, for example, if we have a grammar like this, what can we do? So far we have seen examples like this, okay, but if you have examples like this, what can be done? Okay, this is already in CNF, no problem, no useless, no unit, no lambda productions and all. So instead of this, we may introduce a new production A1, new variable A1. So A1 gives A will be a new production, S gives A1A, no problem, B gives B will be there. But what about this production? This is not in CNF, right? On the right hand side we can have only 2 variables, but we have got 4 variables here. So instead of that, we can substitute the variables. Okay, for these 2 variables we can use, say for example, for A2 we can have AB, we introduce a new variable A3 for AA. Okay, and now this production will become A3 A2. So instead of this, we can have a production like this. Okay, so that will solve a lot of problem, lot of time. Okay, so for this A we have got A1, this is already in CNF. For this production we have introduced new variables. For AA we have introduced A3, AB we have introduced A2 and by substituting A3 and A2 we will get A gives A3 A2, which is C in CNF. Okay, so this is how we can tackle the situation if we have more than 2 symbols on the right hand side. Okay, similarly if we have a production like this, okay, and you can introduce new variable for this A, so it will become A1 and sorry, for A1B you can introduce a new variable A2. Okay, so the production of A will become A2. Okay, so conversion of CFG to CNF is fairly simple if you know how to simplify the grammar. Okay, it will be only the introduction of new variables most of the time and the substitution of the corresponding variables in its position. Okay, now let's quickly go through the conversion of CFG to GNF also. GNF means the Greibach normal form. All the production should be of the form A gives A alpha, okay, where A is the terminal, alpha will be part of V star. Okay, alpha belongs to V star. Okay, 0 or more number of variables. Okay, here comes the steps that you need to use to convert a given context-free grammar to its equivalent Greibach normal form. First step is the elimination of left recursion, then the reduction of grammar should take place, then the conversion should take place. Alright, so to eliminate left recursion, we need to identify what is left recursion. Okay, please remember this is one of the important topics when it comes to the designing of compilers also. Okay, what do you mean by left recursion? That's what is represented here, right? The production of grammar is said to have left recursion if the leftmost variable of its right hand side is same as the variable of its left hand side. Very simple. If there is anything like this, then that is left recursion. Okay, the leftmost variable on the right hand side, that is this one, is same as that of the variable on the left hand side. Okay, if these two variables are the same, then it is called as left recursion. Okay, and a grammar containing a production having left recursion is called as left recursive grammar. Again, you need to remember this property. When can we say a grammar as left recursive grammar? If we have a left recursive production. What is left recursion? If the left hand side variable and the leftmost variable on the right hand side is the same, then it is left recursion. Okay, and it is considered to be problematic when it comes to the parsing, top down parsing, because we do not know what is going to happen. Are we going to go for the recursive substitution, or it is going to be something else? Okay, you will be you will be exploring this when you study the compilation parsing phase of the different parsers of compiler design. Okay, so we need to eliminate the left recursion from the grammar. Here we go with the procedure of left recursion elimination. Okay, here we saw the property of left recursion. If these two are equal, then it is left recursion. But how can we eliminate? Here is the formal procedure. If we have a left recursive pair of productions like this, A gives A alpha or beta. Okay, so if these two symbols are same, these two variables are the same variables, then it is left recursion, as we know. Okay, and we have one more production for A which doesn't begin with A. Okay, so this is a left recursive production, this is not. If that is the case, this is how the left recursion is going to be eliminated. Okay, so A will be having B A dash, beta A dash, sorry. So this will become the starting symbol, not this symbol, it can have a combination. Alright, combination of variables and terminals, because it is just CFG. Fine, followed by A dash. A dash can be alpha. Alpha will come from the remaining portion of the first production after this symbol A. Then A dash will come from this slash or epsilon. And this is a formula, and you can call it as a formula with which the left recursion can be eliminated. Okay. And A dash is the new variable that we are going to introduce. So here if you look, the left recursion won't be there. Okay, the leftmost symbol on the right hand side will not be equal to the the symbol on the left hand side. Okay, so this is how the left recursion can be eliminated. We are going to make use of a production which is not having left recursion, and then a new variable will be introduced, and for the production of the new variable we will be having the remaining portion from the left recursion production and the new variable. Okay, followed by epsilon. Here we go. If you are given with a grammar like this, let's try to eliminate the left recursion. Okay, and this grammar has left recursion production. S gives S's. Okay, this S and this symbol are equal, so there is a left recursion. Okay, so we are not going to touch these two productions because they do not have left recursion. So first and foremost thing that we are supposed to do when we try to convert a context-free grammar to its equivalent GNF is the elimination of left recursion. So S gives SS is having left recursion. Okay, so instead of that, what are we going to do? So this is called as S gives SS, X, S, Y, A. If we compare it with the previous one, it will be A, alpha, beta. So beta can be XYZ, sorry, XY, XSY or A, because they are not starting with S. So this alpha can be S as per the previous one, sorry, right? And we are going to make use of this as the starting symbols like this, X, S, Y, and a new variable is going to be introduced. If this A is going to be acting as beta, then we will have a production for that also. P will be a new variable. For that we need to introduce a new variable P, and this alpha will be coming here, then this variable, then epsilon. So we are following the same formula or procedure. Okay, and production which doesn't start with the same variable A will be the starting portion. then a new variable will be introduced. For the production of new variable, the remainder of the left recursive production will be used and the new variable will be used there, then epsilon. Okay, the point is we need to identify the left recursive production first, then we need to eliminate it. Now we have eliminated the left recursion. Let's try. And we are going to simplify the grammar. No useless productions, but we have null production. P can be a null production. Okay, so if you substitute epsilon for this one, it will be x s y. If you substitute epsilon for this p, it will be a. Okay, similarly if you substitute epsilon for this p, it will be simply yes. Okay, we have eliminated the epsilon production also. Null production also is eliminated, and this is how we have got the new set of productions after removing the left recursion as well as the null production. Now let's see which are all the productions are in GNF. What is GNF? Greibach normal form. So this is in GNF, this is also in GNF, this is in GNF. Okay, all these four are in GNF, but these two are not in GNF. Okay, we are here, sorry, we are here. These are all already in GNF, this is in GNF, this is in GNF. Okay, so other productions are not in GNF. So what are we going to do? Instead of this x, we are going to substitute this open parenthesis. For this x also, we are going to substitute this open parenthesis. If we do so, this will become, these two will become the productions in GNF, but these two are not. Okay, so for that, what are we going to do? So P gives SP is not in GNF, so the productions of S is going to be S are going to be substituted. Okay, S has got 4 productions starting with terminal, right? So instead of this S, we are going to substitute the productions like this. All right. Excuse me. So this is what will happen if you are trying to convert a context-free grammar to its equivalent GNF. All right, and you may think that sorry, this is not a simplified grammar. Okay, this still has an unit production, right? So we can replace this S with all the productions of this all the productions of S. That can also happen. Even after that, we will be ending up with the same set of productions. You can try. All right. So this is how we will be converting a context-free grammar to its equivalent Greibach normal form, where all productions should be of this form. A gives alpha, A alpha. A is a terminal. Alpha will be combination of variables alone. 0 or more number of variables. Okay, first one is the elimination of left recursion. What is left recursion? If the first variable on the right hand side is also equal to the left hand side variable, then it is called as left recursion. We have a formula to eliminate left recursion. After elimination of left recursion, we need to simplify the grammar. After simplification, if you have any production not in GNF, we will go for substitution. Here we won't be introducing a new variable most of the time because we will be going for substitution. Okay, so that is how CFG can be converted into its equivalent Greibach normal form. Hope you have got good idea about the normal forms of context-free grammar, and where are we going to use the normal forms, and where the normal forms are very important, that will be discussed in the next session. Thanks for watching.